Good day, everyone. Our topic for today is about torsion. What is torsion? Torsion is the study of how bodies deform under twisting moments. Torsion is the deformation that results when a structural member is subjected to a twisting moment torque about its longitudinal axis. It produces rotation, shear stresses with cross sections, and an angle of twist along the member's length. Twisting moment T causes shear deformation, shear strain Y. Here's a picture of a torsional stress. We can see that the polar moment of inertia J for solid rod is given. J is equals to pi d raised to 4 over 32. So the key formulas are T over J equals to T over R of a cylinder over polar moment of inertia over L, torque is measured in Newton metri, polar moment of inertia in measured in raised to the power 4, radius of cylinder polar moment of inertia, and torsional stress measured in Pascal or Newton per meter squared. For shear stress measured in Pascal or Newton per m squared. G for shear modulus measured in gigapascal, theta for angle of twist measured in radians, and lastly R for radius of cylinder measured in meters. Torsional stress formula is given. Torsional stress is equals to torque times radius of a cylinder over polar moment of inertia. So torque is measured in Newton metri, polar moment of inertia in meter raised to the power 4, radius of cylinder in meters, and torsional stress in Pascal or Newton per meter squared. So for the formula of polar moment of inertia is given J is equals to pi times radius of cylinder raised to 4 over 2 equals to pi times diameter raised to 4 over 32. So we are going to use pi times diameter raised to 4 over 32 if the rod is solid. Next, for the formula of a twist angle, it is given twist angle is equals to torque times length over shear modulus times moment of inertia, and twist of angle is measured in radians. We have assumed that the material is linearly elastic. Hooke's law can be applied to determine the shear strain as follows. Shear stress is equals to shear modulus times shear strain, where shear strain is measured in radians. We can get shear strain using the formula Y is equals to angle times radius of cylinder over length of the bar. For shear modulus, G is equals to torque times length over theta times polar moment of inertia. Now let's move to the example problems. So for our example problem, a brass rod is 500 mm long. A torque of 20,000 Newton millimeter is applied, causing an internal reaction. If the product of the modulus rigidity and the polar moment G times J is 8 times 10 raised to 8 Newton millimeter squared, what is the angle of the twist? So we have a given of torque is equals to 20,000 Newton millimeter, length equals to 500 millimeter, and our modulus of rigidity times polar moment is equals to 8 times 10 raised to 8 Newton millimeter squared. So to solve for our angle of twist, we're going to use the formula theta is equals to T times L over G times J. 20,000 Newton millimeter times 500 millimeter is equals to 10 million. And 8 times 10 raised to 8 is equals to 800 million. So we're going to divide 10,000. So 20,000 Newton millimeter times 500 millimeter is equals to 10 million. And 8 times 10 raised to 8 is equals to 800 million. So we're going to divide 10 million over 800 million. So we're going to get 0.0125. So that is our angle of twist.
So, good morning, everyone. So, let's discuss on a topic from the fundamentals of deformable bodies. First, let me introduce my name, James Carlin Kindao, and my instructor is Engineer Jigs. So, torsion of circular shafts. Torsion is the twisting of a shaft caused by an applied torque twisting moment around its axis. A circular shaft, like a drive shaft or rod, experiences torsion when forces try to rotate one end relative to the other end. And torsion of circular shafts are circular, homogeneous, and deform elastically within the proportional limit. Uh, Uh, Other considerations, which are hollow shafts, are more efficient in resisting torsion than solid shafts of the same weight, as material is further from the axis where stress is higher. So let's proceed. Formulas. Let's proceed to the formulas. In torsion equation, we have torque over polar moment of inertia equals shear stress over radius equals modulus of rigidity times angle of twist over length. And in the right side here, we have on how to get stress formula. We have shear stress equals torque times oh, I'm sorry, let me rewind. I'm wrong. The shear stress equals torque times radius over polar moment of inertia. So this is how to get stress. And this one we have to get an angle. To get the angle, we have torque times length over polar moment of inertia times modulus of rigidity. And here, where polar moment of inertia equals pi d pi d raised to the power of 4 equals 32 on how and this is where we got solid. And here, this is where we get hollow shaft. This is the formula of hollow shaft. uh, and if I remember correctly, this is the formula of solid shaft. Yep, solid shaft. And let's proceed to the problems. In this problem, we have example 27.5. A hollow shaft of external and internal diameters as 100 mm and 40 mm is transmitting power at 120 rpm. Find the power the shaft can transmit if the shearing stress is not to exceed 50 MPa, or uh, let's just call let's just call it MPa. And this one, the bigger one, is the external diameter, and the smaller d, which is this, is the internal diameter, and we got 40 mm. And in external we have 100. Speed of the shaft n equals 120 rpm, and allowable shear stress is 50 MPa, equals 50 Newton per millimeter squared. We know the torque. We know the torque the shaft can transmit. So to find power, we first need to calculate the maximum torque, which is the T. The shaft can transmit without exceeding the allowable shear stress. So let's find the answer. So first, let's um, you we put pi over 16 times shear stress times opening bracket external diameter raised to the power of 4 minus internal diameter raised to the power of 4 over external diameter, close bracket, equals pi over 16 times 50 times open open bracket uh, opening parenthesis 100 close parenthesis raised to the power of 4 equals, oh no, minus opening bracket 40 and closing bracket raised to the power of 4 over 100, then close bracket, we put Newton millimeter, and this is the answer when we input it in the calculator. 9.56, and let's times it with 10 raised to the power of 6 Newton millimeter, and we got the answer, which is 9.56 kilonewton per meter. And there you have it. Thank you for listening.
So yeah, let's talk out here about power transmission. What are transformers? A transformer consists of three major components: an iron core shaped in U or square shape, a primary coil wound around one side of the iron, a secondary coil wound around the underside of the iron. This is the primary coil, and this is the secondary coil. Next page. The alternating current in the primary coil generates an alternating magnetic field in the iron core. This alternating field passes through the secondary coil and includes an EMF in the secondary coil. The ratio of the voltage across the secondary to the voltage across the primary coil is equal to the ratio of the turns. Vs over Vp equals Ns over Np. Primary coil, secondary coil. Voltage stepping. The purpose of the transformer is to either step up or step down a voltage. When stepping up a voltage, the output voltage is greater than the input voltage. In a perfect transfer of magnetic flux and consumed in energy, power is conserved input power, output power. Pn equals V out, Vp Ip equals Vs Is. Ip over Is equals Vs over Vp equals Ns over Np. It can be seen that in a step-up transformer, the number of secondary turns exceeds that in the primary coil and the current is stepped down by the same factor by which the potential difference is stepped up. Almost all electrical appliances other than lights and motors connected to a domestic supply use a transformer. Measuring AC voltage. When comparing DC and AC power supply, it is necessary to carry out conversion to make a true comparison. Below is a regular sinusoidal AC voltage as could be produced by a generator. The peak voltage is 339 volts. The peak-to-peak voltage (VPP) is defined as the difference between the maximum and minimum, in this case positive 339 to negative 339 equals 679 volts. RMS voltage is the square root of the mean of the square of the potential difference. This is complicated value is used because it gives the value of DC potential difference that has the same heating effect as the alternating potential. In the case above, the DC potential difference that will transfer the same energy is given by square root P 0 to the power of 2 over 2 where V0 is 339 volts. In Australia, the RMS is equal to 240 volts. Any AC current can be given an RM, RMS equivalent value in exactly the same manner. When doing calculations involving power, always use the RMS values unless otherwise stated. Domestic wiring. We have here the main switch. This is circuit breaker, power point, and the neutral bar. Two wires come from the power pole to the house. The active wire is 240 volts RMS. The neutral wire is 0 volts and it's connected to the ground. The cable from the pole goes first to a mains connection, which contains a fuse in the active wire. Then it is connected to the switchboard or fuse box. A main switch is placed in the active wire so that the power can be easily cut in case of emergency. Several lighting in power circuits originate at the switchboard and each has a fuse or circuit breaker, so the individual circuits can be isolated and cut. The neutral is connected to the neutral bar in the switchboard, which is earth. The neutral bar has connection to each power and lighting circuit. Third wire on earth also goes to each circuit. The earth wires are connected into the ground, often by a water pipe or metal stick. They serve as a safety feature, and the earth wire is connected to the metallic base of an appliance. If this case accidentally becomes amplified, the current flow harmlessly to earth and possible blows of fuse in the process. The current will flow to the earth because it will always take the path of least resistance. The fuse is designed to blow and break the circuit if too much current flows at any time. The earth pin on 3-pin plugs is always longer than the active and neutral to ensure that the appliance is always earthed when plugging in. RCD can always be used on a circuit board. They do not provide protection against overload or short circuit conditions. To be effective, the RCD must operate very quickly at a low earth leakage current. Tools designed to protect human life are engineered to trip out with an earth leakage current of 300 milliamp, milliampere within 200 ms, and at a higher earth current of 150 milliampere milliamps. They will trip in less than 40 ms. These limits are well inside the safe zone within which electrocution of or fire will not be expected to occur. In Australia, residual current devices have been mandatory since 1991 in new houses on all power and lighting circuits. Vertical distribution system. Resistance of power lines is proportional to the length of the lines. The longer the wires, the more important the transmission losses become. The larger the diameter of the wire, the less the resistance, but the greater the weight, cost, and higher the supports need to be. It is paramount to reduce the power losses in cables. P loss equals V loss times I transmission. V loss equals I transmission times R. P loss equals I transmission to the power of 2 times R. Transmitting at a high voltage in relatively low current reduces power losses. This requires stepping up the voltage at the power station and stepping it down for industrial and domestic use. In order to transmit large blocks of power over transmission lines, it is necessary to use a high voltage 500 kilovolt. Only then can the current be kept down to a reasonable level, 1 times 10 to the power 4 ampere. If the was transmitted at 250 volts, it would require a current of 2 times 10 to the power 7 amps to supply the power to Melbourne. The power is transmitted in current and AC current because of its current voltage level over long distance. AC is always advantageous in its ability to be transformed either up or down. In contrast, DC current is unable to be transformed, necessitating transmission of large amounts of power, which would increase the energy loss resulting from large voltage drops. Typically, the power is sent from generating station at voltage as high as 500 kilovolt. As it arrives at terminal station, it is stepped down to 66 kilovolt and then down to 11 kilovolt at a substation. Pole, pole transformers further step it down to 415 and 240 volts for domestic use. Its various stages power is taken from the system and rectified into 600 volts or 1500 volts DC for public transport. Power is always transformed into other AC voltage for specific uses in industry. Power losses in transmission lines need to be considered in some questions. The power is not actually lost, it is dissipated into heat which becomes unusable. The power supplied to the consumer is equal to the power supplied at the start minus the power loss in transmission. That's all. Thank you.
Good day, everyone. I am John Vincent Relabo, and today I will present the topic flank bolt coupling, which is an important component in mechanical power transmission systems. In this presentation, we will analyze the working principle of flank bolt coupling, its main mechanical components, the stress analysis involved in torque transmission, the engineering equation used to determine torque capacity, and finally an example problem to illustrate the calculation. Let's proceed now to the definition of a flange ball coupling. It is commonly used between connection of two shafts. It consists of flanges rigidly attached to the ends of the shafts and bolted together. It consists of key components. A shaft. A shaft is a rotating cylindrical machine element designed to transmit torque and rotational motion from a power source such as an electric motor or turbine to another mechanical component such as a pump, gearbox, or compressor. However, in practical mechanical systems, shafts are rarely manufactured as one continuous piece because machines must allow assembly, disassembly, maintenance, and replacement of components. Because of this, engineers use a mechanical device called a coupling. We have another key components, which is the bolts. Bolt is a key mechanical element used to connect two rotating shafts so they can transmit power smoothly. In this setup, each shaft is fitted with a flange, and these flanges are aligned face to face and secured using multiple bolts. Without these bolts, the flanges would separate or slip, preventing effective power transmission. Thus, the bolts are not merely fasteners but essential components that maintain structural integrity and enable smooth, reliable mechanical operation. So we have here another. So the two examples shown illustrate different applications. The metallic coupling on the left is typically used in industrial power transmission system. Example, machinery, automotive drives, where strength and precision are critical, while the colored pipe coupling on the right serves fluid handling systems. Example, water and gas pipelines, prioritizing sealing and structural integrity under pressure. Design is governed by principles like torque capacity, based on bolt shear strength and material properties, alignment tolerances, and material selection tailored to use cases, from steel for high torque to stainless steel for corrosion resistance. Let's proceed now to the main parts. A flange bolt coupling usually consists of these parts. First, two flanges. Each shaft has a flange fixed to its end. The flanges face each other when assembled. 2. Bolts and nuts. Bolts pass through holes in both flanges, and they hold the flanges tightly together. So 3. Key and keyway. A key fits into slots in the shaft and flange hub. This prevents slipping and ensures torque transmission. It presents the torque capacity formula for a coupling with one circular row of bolts. T is equals to shear force times Rn equals to pi d squared over 4 times T times Rn, which calculates the maximum turning power the coupling can safely handle. Here, T is torque capacity, P is the shearing force per bolt, determined by multiplying the bolt's cross-sectional area, where d is bolt diameter, by the material's shear strength. R is the radius of the bolt circle, distance from the flange center to each bolt, and N is the number of bolts in the row. In short, total torque is found by multiplying each bolt's force capacity by its distance from the center. For couplings with two centric rows of bolts, the total torque capacity is the sum of each row's contribution, given by T equals to P1 times R1 times N1 plus P2 times R2 times N2, where P1, R1, and N1 and P2, R2 N2 represent the shearing force per bolt for the first and second rows respectively. A diagram illustrates this arrangement under where P equals shearing force, R equals radius of the bolt circle, and N equals number of bolts in the bolt circle. We have here the relationship between P1 and P2 can be determined from the fact that the comparatively rigid flanges cause shear deformations in the bolts that are proportional to their radial distances from the shaft axis. This section explains how to find the relationship between the shearing forces P1 and P2 in bolts from two concentric rows of a flange bolt coupling. This proportionality creates the shearing strain relationship Y1 over R1 equals Y2 over R2, where Y1 and Y2 are the strains in each row bolts. Using Hooke's law for shear, G equals shear strength over Y with G as shear modulus, T as shear stress, and Y as strain. We substitute Y equals Tg into the strain ratio to get T1 over G1 times R1 is equals to T2 over G2 times R2. Since stress is equals to P over A, where P is shearing force and A is bolt's cross-sectional area, this can also be written as P1 over divided by A1 over G1 times R1 is equals to P2 divided by A2 over G2 times R2. When bolts in both rows are identical, A1 is equals to A2, and same material, G1 equals G2. The A and G terms cancel out, leaving the simplified proportionality. P1 over R1 is equals to P2 over R2. This means shearing force on each bolt is directly tied to its distance from the shaft center, ensuring load is distributed appropriately based on position. Done in our discussion, let's apply and analyze some problems. So we have here the first example. A flange bolt coupling consists of 10, 20 mm in diameter bolts spaced evenly around a bolt circle 400 mm in diameter. Determine the torque capacity of the coupling if the allowable shearing stress in the bolts is 40 MPa. The torque capacity calculation starts with the formula T equals pi d squared over 4 T times Rn, which combines the shear area of each bolt, allowable shear stress, bolt circle radius, and number of bolts to find the maximum torque the coupling can transmit. Here, D is equals to 20 mm is the bolt diameter. T is equal the shear stress equals to 40 MPa or mega Pascal or 40 Newton per square millimeter is the allowable shearing stress. R is equals to 200 millimeter convert to meter, which is 0.2 meter is the bolt circle radius. It is the half of the 400 millimeter diameter, and N is equals to 10 is the number of bolts. First, we calculate the shear area of one bolt using pi d squared over 4, which equals to 100 pi or equivalent to 314.16 square millimeter. Multiplying this area by the allowable shear stress gives the shear force per bolt. 40 times 314.16 is equals to 12,566.4 Newton. To find total torque, we multiply this force by the bolt circle radius in meters and the number of bolts. 12,566.4 times 0.2 times 10 is equals to 25,132.74 Newton per meter, or approximately 25.13 kilonewton per meter. This value represents the maximum torque the coupling can handle without exceeding the bolt's allowable shearing stress. So that's all for today. I hope you learned something. So see you next video.